Okay, let's unpack this. Imagine you're an AI researcher, right? Staring at your monitor, probably fueled by, I don't know, endless coffee.
Oh, yeah, and maybe the existential dread of quadratic complexity.
Exactly. And you got your trusty transformers. They're brilliant, they're groundbreaking, but wow, are they compute hungry?
Total giants. And then you see these newcomers, the state space models, the SSMs.
Right, the SSMs. Lean, efficient,
Mm.
maybe a bit limited sometimes in seeing the whole picture.
Yeah, that's the perception. So what's a researcher supposed to do? You're stuck between this rock and a hard place.
Seems like a tough choice.
Well, what's really fascinating here, and the source material really drills down on this, is that the Falcon-H1 team, they didn't actually see it as an either-or choice.
Ah, okay.
Yeah, they realized the problem wasn't about picking a winner. It was about understanding, the complementary strengths of both architecture.
So blending them.
Precisely. Blending them side by side, in parallel. Think of it like a carefully orchestrated dance. You've got attention for those really sharp, crucial, long-range
The
connections.
stuff Transformers are great at.
Exactly. And then you have the SSMs handling the smooth, really efficient flow of sequences. And they didn't just guess, they meticulously tweaked the ratio, letting each part do what it does best.
So they call it a hybrid? You might just call it balance.
That's a good way to put it. Balance.
And today we're diving deep into Falcon-H1. This is a model that seriously promises to redefine what efficient even means in the world of large language models.
It really does.
Our mission for you, listening in, is to pull out the most important nuggets of knowledge from these, frankly, astonishing innovations, the things that kept this system from just collapsing under the weight of traditional LLM limitations.
Yeah.
You're about to hear how this team tackled some of the biggest challenges in AI and built what they're actually calling the blueprint for smarter models.
That's their claim, and it's a bold one.
Okay, so here's where it gets really, really interesting. Falcon-H1 didn't just, slap two different things together.
No, definitely not.
They engineered this deeply integrated, genuinely hybrid mixer block. It's not just some theoretical idea. They're actually using both attention heads and Mamba 2 heads at the same time, in parallel.
Right, Mamba 2 being a specific type of SSM.
And the really clever part, I think, is that you can adjust the amount of attention versus Mamba heads independently.
Yeah, that independent tuning is key. It allows for this incredibly precise optimization depending on what you need the model to do.
So for you, the person may be looking to use this AI. What does this really fundamental design choice actually mean in practice?
Well, connecting it to the bigger picture, this parallel design, it's pretty revolutionary. It's the core reason Falcon-H1 gets faster inference.
So quicker answers, less waiting.
Exactly. And significantly lower memory usage, which is huge.
Sure.
Plus, really strong generalization across all sorts of different tasks. It's a very deliberate, meticulously engineered choice. It moves beyond the limits of models that are just transformers or just SSMs.
Right, you get the best of both.
You really do. You get that detailed precision and the sort of global understanding from attention for those critical long-range connections. And you get the sheer computational efficiency of the SSMs for mixing sequences more locally. They didn't just stumble on this. The team ran tons of experiments, systematically testing different ways to combine them, really fine-tuning that balance in their unique mixer block.
So it was crucial for getting that performance without sacrificing the efficiency.
Absolutely crucial. It wasn't an afterthought. It was foundational.
Okay, now prepare for something kind of jaw-dropping. The Falcon-H1 team trained models from 0.5 billion parameters, tiny, really all the way up to 34 billion.
A pretty wide range.
And here's the kicker. That 0.5B model, it actually matches the performance of many 7 billion parameter models from 2024 on tough stuff like reasoning, math, even code generation.
That's impressive scaling.
And it gets better. Their 1.5B deep variant, and the key here is deep, meaning they stack more layers instead of just making it wider.
Right, depth versus width.
That model goes toe-to-toe with state-of-the-art models in the 7 to 10 billion parameter range. I mean, this sounds almost impossible. How can smaller models perform that well?
Yeah, it really raises that important question. How do you get such outsized performance? And if the source material is clear, this parameter efficiency isn't magic, it's design.
Strategic design.
Exactly. Unlike a lot of the giant models that just hoover up unbelievable amounts of data, the Falcon-H1 team used, relatively speaking, a fraction of that data, but they focused intensely on its quality.
Quality over quantity.
Precisely. So every model in the series is engineered to match or even beat the performance of models at least twice its size.
Which makes them super attractive for, say, running AI on your phone or other edge devices.
Absolutely. Low resource environments, edge deployments, all without really compromising capability. And they specifically found that prioritizing depth, adding more layers, consistently gave them better overall quality.
Like that 87-layer 1.5B deep model you mentioned.
Yeah, that one dramatically outperformed even wider models. It shows this conscious trade-off they made, really pushing for deeper reasoning and understanding over just, brute size.
It's a real shift from just bigger is always better.
It's smarter design is better.
Okay, let's talk context length. Think about this. 256,000 tokens.
Yeah, that number jumps out.
I mean, put that in perspective. That's enough to feed it an entire book or a massive code base or like a year's worth of customer service chats all at once.
No more chopping things up.
Exactly. No more chopping up critical documents. No more the AI forgetting the beginning of a long conversation halfway through. Long legal documents, dense code repositories. It handles them easily.
And the performance.
That's the astonishing part. Throughput, like how fast it processes, barely dips. And memory usage stays incredibly lean.
Wow.
So for you, the listener, this means you could actually understand an entire legal brief or analyze massive research papers, maybe debug a whole software project without losing that vital context, without having to break it into little pieces.
It's like giving the AI a perfect long-term memory.
Kind of, yeah.
Yeah.
So how on earth did they pull that off? That sounds like an engineering nightmare.
Well, it's definitely an engineering feat. What's fascinating here is how they did it. The team implemented these advanced infrastructure innovations. They call them context parallelism, or CP,
Okay.
and mixer parallelism, or MP.
CP and MP.
Got it. So context parallelism, CP, is basically how they managed to process these huge context windows without just melting a single GPU.
Right. You can't load a whole library into one brain instantly.
Exactly. So they found this clever way to distribute the workload across many GPUs, many readers, if you will, who then efficiently pass along the key ideas. For the SSM layers, they use what's called a chunk-wise state passing schedule.
Sounds complex.
It basically means each processing unit handles its own section and then passes only the necessary info to the next one. It keeps memory use linear, efficient.
Okay, that makes sense. And mixer parallelism, MP.
Right, MP. That dynamically assigns different GPUs to handle either the Mamba operations or the attention operations. This mix-and-match approach led to a really substantial speed-up, 1.43 times faster training throughput.
Wow, nearly 50% faster.
Yeah, and it also massively speeds up inference, making it super responsive for things like real-time applications where low latency is key.
But the infrastructure isn't just bigger, it's smarter. It adapts.
It intelligently adapts. That's the core idea.
All right, this next point, I think this is a huge deal for anyone working globally. Most LLMs, let's be honest, are English first.
Very much so. Other languages often feel like an add-on.
Yeah, the quality varies wildly.
Right.
Not Falcon-H1. This model speaks 18 languages fluently right out of the box. Arabic, Chinese, Hindi, Russian.
You name it.
And crucially, it wasn't an afterthought. No, that's the key. This multilingual ability was built into the tokenizer, the core vocabulary, and the training data mix from day one.
Foundational again.
Yeah. So it doesn't just translate words. It can actually reason across different scripts.
Yeah.
It can tackle complex math problems written in Hindi or understand and generate code in Korean.
It genuinely doesn't flinch, whatever the language.
That's incredible.
Yeah.
How do they ensure that level of quality across so many languages?
Well, this deep dive really highlights that the multilingual tokenizer, the thing that breaks text down for the model, was trained on incredibly diverse language datasets.
Makes sense.
And this strategic approach means it can actually scale effectively to over 100 languages eventually.
Wow.
The data itself comes from everywhere. Common Crawl, Wikipedia, academic papers on Archive, online forums, tons of open source books.
A really broad mix.
Yeah, a comprehensive strategy to make sure it performs robustly across all these different linguistic and even cultural contexts. The team actually talks about doing detailed studies on tokenizer training. Yeah, finding that just throwing more data at it doesn't automatically make a better tokenizer. There's sort of an optimal range depending on your vocabulary size. They even added specific latex tokens.
For math notation.
Exactly, which significantly boosted its performance on math benchmarks. It just shows this really thoughtful, ground-up approach to making truly global AI.
Okay, it seems like this team really enjoys rethinking the fundamentals, the basic rules of AI training.
They definitely aren't afraid to question established practices.
Like they revisited core components, something called ROP, rotational positional embeddings.
Right, ROP. It's how models understand where words are in a sequence, which is pretty fundamental.
And they used an unconventionally high base frequency, 10 to the power of 11. That sounds very specific.
It is specific, and maybe a bit technical, but why it matters to you, the user, is actually quite cool. It brilliantly simplifies scaling the sequence length later on.
Ah, okay. So if you want to use longer context after the model is already trained.
Exactly. Or during continuous pre-training, you don't need complex modifications later. It just works. It makes the model incredibly flexible for future growth or adaptation.
Less hassle down the line.
Much less hassle. And it also brings up this important question about something called maximal update parameterization, or MUP.
MUP? Okay, sounds advanced.
It is. It's a sophisticated technique meant to make training these massive models more predictable and stable as they get bigger.
Right.
But again, they didn't just use UP, they augmented it. They added these finely tuned multipliers. Essentially, they shifted the scaling logic away from just tweaking the learning rate and weight decay.
Which are the usual knobs you turn.
Right. They shifted it directly into forward multipliers inside the model's architecture.
Okay, what's the benefit of doing that?
The benefit is huge for developers. It allows all the models in the Falcon-H1 series, no matter their size, to be fine-tuned or continuously pre-trained using the exact same learning rate and weight decay parameters.
Wait, really? The same settings for the 0.5B and the 34B?
The same base settings. Imagine how much simpler that makes things.
That takes away a massive headache.
It really does. And they also introduce these concepts they call effective learning rate and effective weight decay. It basically gives you a more intuitive way to understand and tune these crucial training settings.
Making it easier to get it right.
Exactly. It's all about tailoring the training dance, moving away from a complex one-size-fits-all thing to something much more elegant and consistent across the whole model family.
That sounds incredibly practical.
Oh.
Okay, so after all these innovations, the hybrid architecture, the efficiency, the context length, multilingual, the training, tweaks the big question. How did Falcon-H1 actually perform?
Right. The proof is in the pudding, as they say.
How did it stack up on the benchmarks?
Well, across the board, on rigorous tests covering various tasks and scales, the base models really shine. And the instruction-tuned models, they absolutely dazzle.
So the ones fine-tuned for following commands?
Precisely. The 34B instruct model consistently rivals and often outperforms much larger 70 billion parameter giants.
Even models twice its size.
Yeah, particularly in critical areas like science, general reasoning, and complex conversational abilities. And those smaller models we talked about, like the 1.5B deep.
The one that punches above its weight.
It really does. It matches or beats models anywhere from 2 to even 5 times its size on many tasks. These aren't just small improvements, they're fundamental leaps in efficiency.
Wow. So the performance claims hold up.
If we connect this to the bigger picture, the point is crystal clear. This isn't just about getting high scores on leaderboards.
It's about the real-world impact.
Exactly. It's profound. These innovations mean models like that Falcon-H1 1.5B deep can actually be deployed and run effectively on edge devices, your phone. Maybe a sensor doing jobs that previously needed a much beefier, like 10B parameter model running in the cloud.
That opens up a lot of possibilities.
It really does. It means you can process those incredibly long documents, analyze whole books, sift through dense code bases without the model, breaking a sweat or losing the plot. It means having one single model that understands, reasons, and talks fluently across 18 different languages. And maybe most importantly,
what's that?
All these advancements are released under open source licenses. No walls, no gates.
Truly open.
Yeah. It's about building a bridge between efficiency and raw power, between what we used to think of as small models and genuinely big capabilities. And they've been really transparent, too, conducting rigorous open evaluations against other top models, making sure the claims are reproducible and fair.
Okay, so what's really striking here, the big takeaway, seems to be their bold claim.
Yeah.
The future of AI doesn't necessarily need bigger models.
It needs smarter ones.
And the Falcon-H1 team genuinely believes they've built that blueprint.
That's the message.
And this deep dive into their innovations, it really shows how strategic, intelligent design, not just brute force scaling, can lead to these kinds of groundbreaking advancements. It really redefines what's possible.
It absolutely does. And this raises, I think, an important question for you, our listener, to kind of chew on. As these AI models become so much more efficient, so much more accessible, how might this blueprint fundamentally change how you interact with and use AI, whether it's in your daily life or in your work?
Will it spark completely new apps on devices we never thought could handle complex AI?
Maybe. Or will it just fundamentally shift how we approach information, how we process it, understand it, generate it in everything we do? It's something to think about.
Yeah.